All right, so for example number 35 here, we're going to read the problem first, and then we will create our table, and then we will solve the problem. So it says, how many cubic centimeters of a 25% antibiotic solution should be added to 10 cubic centimeters of a 60% antibiotic solution in order to get 30% and a 30% antibiotic solution? Now, not only do these come up in chemistry, but nurses and doctors and pharmacists deal with these kind of mixture problems quite often as well. So those are specific fields that you will actually see them in practice. So I'm going to have the volume here, I'm going to have the percent, and I'm going to have the amount, and this one I'm going to call the amount of pure, and this time it's antibiotic. So this is antibiotic, and I'm just going to do antibio there for us. Okay, now what we have when we have these mixture chemistry problems is that we have a weak solution, we have a strong solution, and then we have the mixture. Now what you should realize is that the mixture is always going to be somewhere in between. So when we have two unknown things, that makes it very easy to pick out which one's the mixture because it's the one that has a percentage that's right in the middle. So we can use that as a context clue. So we have how many cubic centimeters, so I'm going to write that up here as the units for our volumes. How many cubic centimeters of a 25% solution should be added to 10 cubic centimeters of a 60% solution? So we have a 25% as being our weak, and we have a 60% which is being our strong, and we're getting a 30%, and you see 30% is right in the middle, so that identifies it in another way as the mixture. Now we're adding to 10 cubic centimeters of the strong stuff. So what we have going on here is actually kind of a different setup than we've seen before. The weak is our unknown, and this time the mixture is our unknown. And then we're going to use that that percentage setup. So volume times percentage is going to give our amount of pure. So X times the 25%. 25%, remember, must be used as a decimal in order to operate on that. So 0.25x, and then 60% of the times the 10, so 0.6 times 10, and then I'm going to say that that is equal to 6, and then y times 30%, or 0.3y. Now you see we're going to get one equation from here, and we're going to get a second equation from here. So we have x plus 10 is equal to y this time. And then the next equation, 0.25x plus 6 is equal to 0.3y. And now we can use substitution because this is our expression for y, and it can go in here to solve it. So we have 0.25x plus 6, and that's equal to 0.3 times x plus 10. And so now we can solve that with or without clearing. It's totally up to you. And then we can get our answer here. So solving this now, I'm going to change colors. So let's go ahead and distribute here. So we have 0.3x, and then we have 30 with one decimal, so 3 there. So that's our simplification. Now we'll bring our variables together on the right-hand side. That's where they're actually larger. So I'll do that. And that's going to give us that 6 is equal to 0.05 x plus 3. And then we have minus 3 here and minus 3 here. So now we have 3 is equal to 0.05x. And that's where I actually a lot of times will clear this. So 2 places to the right here and 2 places to the right here. So I end up with 5x is equal to not just 3, but 300. And that makes it easier for me to solve without a calculator. 5 will go into 36 times and 0, 0 times. And so this is 60 cubic centimeters of, and this is the